In this video, we're going to cover section 3.9 on related rates. So these are application problems for the most part that involve implicit differentiation. And they show us how to solve problems in which the derivatives of two separate quantities are somehow related. So the two objectives are to learn the process of solving related rate problems and then solve applied problems that involve these types of rates. All right, so our first example is just a related rate problem that we're just given information without really any context. So given the function y equals 3 square root of x, find the derivative of y with respect to t. Notice this variable here is t, which is not the variable involved in our given function, when x is 9 and dx dt is -4. Okay, so what's happening in a related rate problem is you have a relationship between more than one variable. So our two variables here are x and y. So you're thinking of both the quantities x and y as functions of a third variable t. In applications, t normally represents time. Okay, so we're going to think of this as y changes as time changes and x changes as time changes. So y has a derivative with respect to time, and x has a derivative with respect to time. Okay, so we want to find, they're asking here to find the derivative of y with respect to time when the value of x is 9 and when the derivative of x with respect to time is -4. All right, so we're given the relationship and we're told what we need to find. So our first step here is to differentiate implicitly the function we're given with respect to t. So we're going to, before we utilize any of this other information, we're going to take our function that relates our variables and find the derivative with respect to t. So in other words, we're going to take the derivative with respect to t of y, and we're going to take the derivative with respect to t of 3 squared of x. So take the derivative with respect to t of both sides. All right, so what this means here, this side is just the derivative with respect to t of y, which is eventually we're going to write down dy dt. This side, the derivative with respect to t of this function, we're going to first write this as x to the 1/2 so we can follow our derivative steps. So then when we take its derivative, we thinking of x as being a function of t, so this is where implicit comes in. So the 3 stays in the front, we multiply, we bring the 1/2 down, so 3 times 1/2 is 3/2 x, and then we subtract 1 from this exponent, giving us -1/2. But then because x changes with time, we have to follow it with the dx dt. So then kind of the sort of a difference that you're going to see here compared to the implicit section is every time you differentiate any variable, you have to multiply it by its derivative with respect to t. So anytime I differentiate x, I have to write down dx dt, or multiply your derivative by dx dt, and anytime you differentiate y, you'll do the same. So that's because of the chain rule. All right, so this left side was the derivative with respect to t of y, which is just basically the derivative of y is 1, so it's 1 dy dt. This is what we get over here. We get 3 on top, 2 on bottom. This moves to the bottom as a positive 1/2, so a square root on the bottom, and then our dx dt. So we do all that first. Now, after we've done all that, now we're going to plug in what we're given and figure out what we need to find. So we're asked to find dy dt. So we're looking for the value of this. When x is 9, so we're going to plug in a 9 for this x. And when the dx dt value, we're going to substitute a -4 for this. So substituting an x value of 9 and a dx dt value of -4, you will get that dy dt equals 3 over the 2, this was the square root of x, we're plugging in 9, and then multiplied by dx dt is multiplying by -4. So the square root of 9 is 3. And then 3 times -4 is -12. 2 times 3 is 6. So this simplifies to -2. The important thing to remember here is you always differentiate first, then plug in given values. Never the other way around. All right, our next example. This is more applied, so we're going to have to come up with our equations that we're going to need and identify what we're given. The restaurant supplier services the restaurants in a circular area in such a way that the radius r is increasing at a rate of 2 miles per year at the moment when r equals 5 miles. At that moment, how fast is the area increasing? All right, so before we can do this problem, we have to understand what formula that we're asked to find the derivative of. So we're asked at a certain moment, how fast is the area increasing, the area of our space, and it says our space was circular, okay? That's going to require that we use the formula for the area of a circle. So based on what we're given here, area of a circle is equal to pi r squared. So area changes as radius changes, so our variables here are a and r. They both change with time. So we're going to differentiate them with respect to time. So this should be dA dt. They wrote r here, but this should be the derivative of a with respect to time equals, pi is a constant, it stays. You drop down the 2r to the first, so you get the pi stays there, 2r to the first, times the dr dt. This should be dA dt. So again, dA dt, 2 pi, and now we're plugging in our r value of 5 when r was 5 miles. And then this, notice it says that r is increasing at a rate of, so that means that if it's talking about increasing or decreasing at a rate, that's giving you a value of the derivative. So since r is increasing at a rate of 2 miles per year, that means dr dt is 2 miles per year. So this dr dt, they're plugging in the 2 miles per year. So your 2 times 5 times 2 is 20 pi. Notice mile times mile is miles squared per year. And if you multiply 20 by pi, that's about 63 square miles per year. And again, that should mean dA dt. They have a typo there. Okay, so let's try another one here. This time we're talking about the shape of a sphere. So a spherical balloon is deflating, losing 20 cubic centimeters of air per minute at the moment when the radius of the balloon is 8 centimeters. How fast is the radius decreasing? So this is similar, but notice instead of talking about area, we're talking about volume. And even though it doesn't mention volume in the problem, our clue here is our unit. So if it's deflating, if you think of a sphere, that's a three-dimensional space, okay? And if it's losing 20 cubic centimeters of air per minute, cubic units represents volume. So this losing 20 cubic centimeters of air per minute is the derivative of volume with respect to time. And that's happening at the moment, or at the moment when the radius of the balloon is 8. So when r value is 8, they want to know how fast the radius is decreasing. So how fast is your radius changing? In other words, what is dr dt? All right, so we're going to use our formula. Volume equals 4/3 pi r cubed is the formula for the volume of a sphere. You may have to look that up. All right, so we're going to start by taking the derivative of both sides. Again, should be with respect to t, so this v should be dv dt. And then over here, when the 3 gets brought down to the front, it cancels with the 3 on the bottom, leaving 4 pi r squared. And then, because the variables are, it's times dr dt. Now we plug in what we were given. So this 20 cubic centimeters of air per minute, because it's a cubic unit, it's the derivative of volume. So that's a 20, and it should be negative. I think they throw the negative in the next line, but since it's deflating, technically this should be negative 20 cubic centimeters per minute equals 4 pi. It gives me here that the radius was 8, so plugging in 8 for r, so 8 centimeters. And then dr dt is what I need to find. How fast is the radius decreasing? In other words, the rate of change of the radius. All right, so the dr dt, if you're solving for that, you're dividing both sides by this 4 pi, and then 8 squared is 64. So notice here the negative shows up. It probably should have been up here also. So the negative because of the decreasing, the 20 cubic centimeters per minute, and then 4 pi, and then 64 cubic centimeters on the bottom to solve for my unknown. And then to clean that up, we could divide 4 into 20 and get negative, this negative stays here, and that would be 5. And this bottom then would just be 64 pi. And then notice a cubic centimeter divided by a square centimeter is just centimeters. So they've converted that to a decimal, so about negative 0.025 centimeters. This should be per minute. Yeah, they don't have the correct unit there. Okay. All right, so let's try another one here. This one involves revenue. So for Lucy Landscaping, the total revenue from the yard maintenance of X homes is given by this function R of X. And the total cost is given by this function C of X. Suppose that Lucy is maintaining 10 homes per day at the moment when the 400th customer is signed. At that moment, what is the rate of change, that means a derivative, of total revenue, total cost, and total profit? Okay, so we're going to be finding the derivative with respect to T of revenue, cost, and utilizing those two things, we can find profit. We got to figure out what these other numbers mean. All right, so they're maintaining 10 homes per day. That's a rate, right? Homes per day. So that's the derivative value. At the moment when the 400th customer is signed, so the 400th customer is in value of X, right? It's X homes. So X is the number of homes, the 400th customer. All right. So the derivative of profit, the derivative of revenue. So the derivative of revenue, let's go back here and look at our revenue function first before we do that. So this derivative would be 1,000, right? dx dt minus 2x dx dt. Right? So 1,000 dx dt minus 2x dx dt is the derivative of the R function. So remember the dx dt was 10 homes per day, so that's the derivative of x with respect to t, and the 400th customer, 400 was the value of x, so we're plugging in the 10 for the dx dt's and the 400 for the x into there, and then just cleaning that up. So we get $2,000 per day. All right, derivative of your cost function would be 20 times dx dt. And then dx dt was 10, so $200 a day. And then we know profit is revenue minus your costs, the money you take in minus what it costs. So that means that the derivative of profit would be the derivative of revenue minus the derivative of cost, just taking the derivative of all terms with respect to t. So we already figured out what this one was, and we figured out what this one was in the previous example, so you're just subtracting your results. So $200 a day minus, $2,000 a day minus $200 a day is $1,800 a day. So that's how fast profit is changing. So the $2,000 a day is how fast revenue is changing. $100 a day is how much costs are changing. So your profit is changing by $1,800 a day at that point. All right. So our section summary here, if two or more variables are related to one another by an equation, we may implicitly differentiate with respect to time. And the result is what we call a related rate. Geometric formulas are often used to help solve a related rate problem. So we saw the example of the circle and the sphere. There are others that can be used, but for your problems that you'll encounter in the homework and possibly on a test, it would be just those two formulas. All right, so that is the end of section 3.9.